When it comes to Saturn, it's hard to summarize just how lucky we were to have the Cassini-Huygens mission. 4 robotic probes have visited Saturn, but of those, Cassini-Huygens has hands down been the most impactful, both literally and scientifically. Its data has provided the bedrock for over 4,000 research papers. It discovered 6 new moons and helped better understand their composition. It survived 20 years, traveling 7 billion kilometers, and spent 13 of those years around Saturn itself, gathering data on Saturn's gravity, magnetosphere, rings, and structure. Cassini kept gathering data right up until the last moment of its life as it plunged into the mustard clouds of Saturn's atmosphere and ultimately broke into thousands of pieces. Couple that with the fact that it provided some of the most jaw-dropping and inspiring images of Saturn and the solar system to date, and you have one incredible mission. The first probe to reach Saturn was the Pioneer 11 probe in 1979. At that time, scientists confirmed that Saturn's largest moon, Titan, had an atmosphere. Knowing this, they realized they had to return to the moon, this time with a lander. Voyager 1 and 2 were already en route to Saturn, so it was too late to include a lander with those missions. Thus, Cassini-Huygens was born. In October 1997, it was launched into space. Getting a spacecraft to Saturn is no easy feat, as the entire trip involved combating the sun's gravity, which constantly tried to pull Cassini back toward the inner solar system. To achieve the necessary speed, Cassini used planets for gravitational assists. It flew by Venus twice before returning to Earth, where Earth's gravity slingshotted it toward Jupiter, giving it the final push needed to reach Saturn. This planetary alignment, which allowed these gravity assists, occurs only once every 600 years, making timing crucial. Cassini came dangerously close to Earth on its second pass, only 1,100 kilometers above the surface at its closest approach. What powered Cassini was equally fascinating. It relied on 3 radioisotope thermoelectric generators, RTGs, which produced energy from about 33 kilograms of radioactive plutonium. This radioactive decay provided Cassini with power, and even until the end of its life, it still generated about 700 watts. The risk, however, was that if calculations had been wrong and Cassini had crashed into Earth, the radioactive material could have exposed the entire planet to radiation. While 33 kilograms spread over the entire Earth would have been a minimal amount, NASA estimated that in the worst-case scenario, it could have caused about 5,000 deaths from cancer. They deemed this an acceptable risk, given the 1 in a million chance of it happening. RTGs were used because solar panel technology at the time wasn't advanced enough to power a spacecraft so far from the sun. With RTGs, Cassini had a long operational life, and it might still be functioning today if it hadn't eventually run out of propellant. Cassini had several key objectives: to study the structure and dynamics of Saturn's rings, explore its moons in greater detail, measure Saturn's magnetosphere, analyze its atmosphere, and conduct extensive research on Titan. This last objective is where the Huygens part of the mission came into play. Huygens was a lander attached to Cassini, designed to investigate what lay beneath Titan's hazy clouds. Built and operated by the European Space Agency, ESA, the probe was about 1.3 meters wide and weighed 300 kilograms. After detaching from the orbiter, it spent 22 days in space before entering Titan's atmosphere. During this time, the only active system aboard Huygens was a wake-up timer, set to activate the probe just 15 minutes before atmospheric entry. What it saw upon waking was extraordinary. The main mission of Huygens was to gather data during its descent, recording atmospheric pressure, composition, wind speed, and other measurements. Because the mission was primarily focused on atmospheric readings, the battery wasn't expected to last long after landing. Scientists had anticipated a possible landing on an ocean or lake, but instead, Huygens touched down on what appeared to be the bed of a dried-up lake. Cassini's mission was remarkably successful beyond scientific data collection. It captured some of the most stunning images of space ever seen, including breathtaking views of Saturn and its moons. Some dedicated individuals have even compiled over 1 million of Cassini's photos to create videos simulating the experience of being aboard the spacecraft. These images are real, only color-corrected and enhanced to show movement, with no CGI involved. As Cassini's fuel began to run low, scientists devised a plan to maximize the remaining time. They sent commands for the probe to perform extremely close flybys of Saturn and its moons, venturing closer than ever before. Beginning on November 30th, 2016, Cassini repeatedly climbed high above Saturn's North Pole before plunging just outside the narrow F-ring, the edge of the main rings, completing 20 orbits in total. Then, on April 22, 2017, Cassini leaped over the rings to begin its final series of daring dives between the planet and the inner edge of the rings. This was the Cassini grand finale, a sequence of loops and dives that brought the probe increasingly closer to Saturn, facing greater risks with each pass until its inevitable destruction. NASA explained the rationale behind this final mission. As Cassini plunged past Saturn, it would collect incredibly valuable data that original mission planners might never have imagined. The spacecraft would map Saturn's gravity and magnetic fields in detail, revealing the planet's internal structure and potentially solving the mystery of its rotation speed. It would also improve understanding of the ring's composition, bringing scientists closer to uncovering their origins. Cassini's particle detectors would sample icy ring particles funneled into the atmosphere by Saturn's magnetic field, while its cameras captured ultra-close images of the rings and clouds. No other mission had ever explored this region so close to the planet. The data gathered would enhance understanding of how giant planets and planetary systems in general form and evolve. At the end of its final orbit, as Cassini descended into Saturn's atmosphere, it ensured that biologically intriguing worlds like Enceladus and Titan would never be contaminated by Earth microbes that might have survived the journey. This decision was both scientifically necessary and poetically fitting, an adventurous, romantic end to a groundbreaking mission. During the grand finale, NASA prioritized unprecedented closeness to Saturn over Cassini's longevity, an easy choice, given that the spacecraft was already running out of fuel. This bold move allowed Cassini to gather the purest data possible before its ultimate demise. The go-ahead to approach the planet closer than ever before, darting in between the rings, raised the question: what did it see? Did this unique perspective reveal anything never observed before? A closer look at some of the incredible sights captured during Cassini's grand finale provides answers. Starting with Saturn's moons, Cassini observed shepherd moons in unprecedented detail. One such example is Atlas, a 40-kilometer-wide moon near the outskirts of the A-ring. What stands out about Atlas is its remarkably smooth surface, largely devoid of impact craters, giving it an unusual appearance. Dust from the rings collects over its surface, particularly around the equator, smoothing it out and contributing to its disc-like shape. A similar phenomenon occurs with Pan, the second innermost moon of Saturn. At 30 kilometers wide and located within the Encke Gap, Pan sweeps up any stray ring particles that drift into its 350-kilometer-wide path, maintaining the gap's stability. Another shepherd moon, Daphnis, though not seen in as much detail, still leaves a visible mark. Only 8 kilometers in diameter, it resides in the narrow Keeler Gap within the A-ring. Despite its weak gravity, Daphnis is strong enough to disturb nearby dust particles as it passes, creating ripples in the rings. These disturbances move not only side to side, but also up and down, casting shadows that highlight their motion. The effect is mesmerizing. Imagine standing on Daphnis, watching as waves trail its orbit, with Saturn and its many moons as a breathtaking backdrop. The rings themselves provided spectacular imagery during the grand finale. One particularly striking image showcases the Janus 21 spiral density wave. What appears to be multiple separate rings is actually just two tightly wound spiral arms looping around the planet. This phenomenon results from the same process that forms spiral galaxies, though on a much smaller scale. The image captures part of the B ring, where the ring orbits twice for every one orbit of Saturn's moon Janus, creating an orbital resonance. The illusion of the image, tilting away at the top left, is due to the way density waves propagate from the planet, with wavelength decreasing with distance from the resonance. The resonance becomes even more fascinating when considering Janus and its neighboring moon, Epimetheus. Every 4 years, these two moons switch orbital positions, and each time this happens, the rings respond by forming a new crest in the waves. NASA explains that the distance between crests corresponds to 4 years of wave propagation, meaning the wave pattern encodes decades of orbital history. The section of the wave in the upper left of the image dates back to the Voyager flybys in 1980 and 1981, when Janus and Epimetheus were first confirmed as distinct objects. This record-keeping resembles the way tree rings mark the passage of time, a remarkable natural archive. Beyond these stunning images, Cassini also documented small propeller-like features scattered throughout the rings. One such image shows both the illuminated and unlit sides of the rings, allowing scientists to study details even at a resolution of about 500 meters per pixel. While the moonlets responsible for these disturbances may be too small to resolve clearly, their influence is evident in the way they connect to the rings via bands of material. Several of these moonlets were observed, none larger than 2 kilometers, and likely with the density of a snowball. Another intriguing discovery was the presence of small, solid objects forming around the E-ring. These objects, possibly shaped by the gravitational influence of nearby shepherd moons, have survived multiple collisions with the ring, kicking up dust that sometimes follows their orbit. Though the objects themselves remain obscured by the debris, their effects are clearly visible. Finally, Cassini turned its gaze towards Saturn itself. With the planet's northern hemisphere in full summer, the famous hexagonal storm around the pole was clearly visible. At its center lies a permanent polar vortex, a massive hurricane-like structure. Interestingly, the pole's color has changed with the seasons, as seen in comparisons with images from 2012, when it appeared much darker. Other storms were also visible across the planet, along with faint atmospheric bands reminiscent of Jupiter, though less vivid in natural light. As Cassini neared its final approach, it captured detailed views of Saturn's horizon, revealing a haze in the stratosphere that dissipated across the planet's curvature. Scientists were particularly interested in the composition of Saturn's upper atmosphere, which Cassini would sample directly during its final plunge. Though it was expected to burn up before reaching deeper layers, the data transmitted in those last moments would be invaluable. In its final week, Cassini continued taking images, some of which were compiled into time-lapse sequences. These sequences, stitched together from countless individual frames, offer a breathtaking simulation of what it would have been like to ride alongside the spacecraft on its final journey. One such time-lapse, captured on September 8, 2017, focused on Enceladus, a prime candidate for harboring life due to its subsurface ocean. Cassini had previously discovered over 100 water plumes erupting from this moon, contributing to the formation of Saturn's E-ring. A later sequence, taken over 14 hours on September 11th, showcased Saturn's rings in stunning detail, with the planet's northern hemisphere bathed in summer light and its hexagonal storm prominently displayed. As Cassini made its last orbits, it also captured final glimpses of Titan, a world it had studied extensively. With its thick nitrogen atmosphere and complex surface, Titan remains one of the most fascinating moons in the solar system. The mission's concluding images, taken just days before its fiery end, serve as a testament to Cassini's unparalleled contributions to our understanding of Saturn and its celestial companions. As Saturn grew larger in Cassini's view, the spacecraft took one final look at Enceladus over a 40-minute period before the moon disappeared behind Saturn's limb. The last image Cassini ever captured focused on the region where it would eventually plunge into the planet's atmosphere. At this point, it was nighttime on Saturn, with the planet dimly illuminated by sunlight, reflecting off its rings. On its final day, photography wasn't a priority. Despite the breathtaking visuals, images consume significant bandwidth, and scientists prioritized real-time data transmission before the spacecraft's destruction. This was a unique opportunity, as no mission had ever probed Saturn's atmosphere directly before. When Cassini first encountered the tenuous outer layers of Saturn's atmosphere, it was traveling at 123,000 kilometers per hour. The spacecraft's remaining fuel was used by its thrusters to keep its antenna pointed at Earth. At this stage, Cassini was about 1,900 kilometers above Saturn's cloud tops. Just a minute later, the thrusters were firing at maximum capacity to prevent Cassini from spinning out of control. The spacecraft was now directly sampling Saturn's atmosphere, but the increasing atmospheric density was also heating it up. Within 10 seconds, the thrusters were overwhelmed, and Cassini began to tumble, severing communication with Earth. Its onboard computers, detecting the uncontrolled spin through gyroscopes and star trackers, likely triggered a safe mode in a last-ditch effort to stabilize power. About a minute later, the spacecraft disintegrated completely, burning up in Saturn's atmosphere. When the final data arrived on Earth an hour and a half later, the mission was declared a resounding success. Cassini had transmitted direct measurements of Saturn's atmospheric composition, ionosphere, dust particles, and magnetic field, with potentially more discoveries still buried in the data. This is the enduring legacy of the Cassini mission. Even years after its end, scientific papers continue to emerge as researchers analyze and re-examine its findings. But what exactly have we learned from Cassini's data in the years since its groundbreaking mission? Some of the discoveries have only deepened Saturn's mysteries. While Saturn is instantly recognizable by its iconic rings and hazy yellow atmosphere, it remains an enigma in many ways. Beneath its obscuring cloud layers lie phenomena that defy conventional models, from its temperature and magnetosphere to the very length of its day. Cassini arrived at Saturn on July 1, 2004, becoming the fourth probe to visit, but the first to orbit and study it in depth. Over its 13-year mission, it collected vast amounts of data using spectrometers, magnetometers, and other instruments. While this wealth of information has been invaluable, it has also raised new questions. Take, for example, the massive hexagonal storm at Saturn's North Pole, a 29,000-kilometer-wide vortex with edges large enough to fit Earth inside. Unlike the rest of Saturn's turbulent atmosphere, this storm remains fixed in longitude, moving with the planet's rotation rather than being swept along by its 1,800 kilometers per hour winds. Scientists still lack a complete explanation for this phenomenon, though laboratory experiments have replicated similar hexagonal patterns on smaller scales. Another enduring mystery was determining the length of a Saturnian day. Unlike rocky planets, Saturn's thick cloud cover obscures any surface features that could reveal its rotation period. The rings, which orbit at varying speeds, offer no clear answer either. Initially, scientists hoped to calculate the planet's rotation by studying its magnetic field, as most gas giants generate magnetic fields through the dynamo effect, where the motion of conductive fluids in the core creates a planetary magnetic field. Typically, this field is slightly misaligned with the planet's rotational axis. But Saturn defies expectations. Its magnetic pole is nearly perfectly aligned with its axis, an arrangement dynamo theory suggests should be impossible. Yet Saturn's magnetic field is not only stable, but also 580 times stronger than Earth's. An alternative method involved analyzing Saturn's radio emissions, which fluctuate in sync with its rotation. Early estimates from Voyager data suggested a day length of 10 hours, 39 minutes, and 23 seconds. However, Cassini's measurements revealed something bizarre. This period varied by about 1% over time, implying either that Saturn's rotation speed was changing, unlikely for a planet of its mass, or that atmospheric effects were distorting the data. Further complicating matters, Saturn's auroras, unlike Earth's, are not solely driven by solar wind. Cassini found that some auroral activity persisted independently of solar activity, suggesting internal processes at work. Additionally, Saturn radiates twice as much heat as it receives from the Sun, a discrepancy only partially explained by gravitational compression. The key to many of these mysteries may lie in Saturn's atmosphere. As a gas giant, Saturn consists mostly of hydrogen and helium, with pressures deep inside compressing hydrogen into a metallic liquid state. Some theories propose that diamond rain forms in these depths, generating heat through friction. The auroras, possibly fueled by charged particles from Saturn's rings and moons, may also contribute to atmospheric heating. This heat, in turn, drives powerful winds that carry charged particles, potentially distorting magnetic and radio wave data. Despite these complexities, Scientists finally pinned down Saturn's rotation period by studying gravitational interactions with its rings. Saturn's imperfectly spherical shape creates subtle ripples in the rings, allowing researchers to calculate a definitive day length: 10 hours, 33 minutes, and 38 seconds. Yet many questions remain unanswered. Future missions like NASA's Dragonfly, set to launch in 2027, will focus on Saturn's moon Titan rather than the planet itself, meaning Saturn's deepest secrets may stay hidden for years to come. Saturn's rings, surprisingly, may be a fleeting feature in cosmic terms. While the planet itself is over 4 billion years old, evidence suggests the rings formed only about 100 million years ago, and they are gradually dissipating back into Saturn's atmosphere. In another 100 million years, they may vanish entirely. This ephemeral beauty makes humanity's window of observation feel all the more precious. Jupiter, the fifth planet from the Sun, stands as a colossal world of storms, radiation, and gravitational dominance. Located just beyond the asteroid belt, it orbits at an average distance of 778 million kilometers, 5.2 astronomical units, from the Sun. With its great red spot, turbulent atmosphere, and immense magnetic field, Jupiter plays a critical role in shaping the solar system. Its composition, internal structure, and influence continue to be key subjects of study, with ongoing missions uncovering new layers of its complexity. Jupiter completes an orbit around the Sun every 12 Earth years. Its axial tilt is minimal, just 3 degrees, meaning it experiences little seasonal variation, unlike Earth or Mars. Similar to Saturn, Jupiter's equatorial radius is larger than its polar radius, giving it a slightly flattened shape. As the largest planet in our solar system, Jupiter is incredibly massive. Its total mass is about 1,000th that of the Sun. While this may seem insignificant at first, considering the Sun accounts for 99.86% of the solar system's mass, Jupiter makes up nearly the entire remainder. In fact, its mass is 2.5 times greater than all other planets combined. This immense mass creates an unusual gravitational phenomenon. The barycenter, the mutual orbital center of mass, between Jupiter and the Sun, lies outside. The Sun's surface, about 1.68 solar radii from the Sun's core. To understand barycenters, consider that all orbiting objects, no matter how small, exert some gravitational influence on their parent body. Normally, this effect is negligible, like the International Space Station orbiting Earth or Mercury orbiting the Sun. However, Jupiter's size and distance make its gravitational pull substantial enough that both the Sun and Jupiter orbit around a shared point in space, located just above the Sun's surface. A simple analogy is balancing a heavy and light object on a stick. The balance point, barycenter, shifts closer to the heavier object. Despite being the most massive planet, Jupiter isn't the densest. If Neptune were Jupiter's size, it would actually be heavier, and if Jupiter were Earth-sized, Earth would be over 4 times denser. Jupiter's diameter is 11 times Earth's, and its mass is 318 times greater. This enormous mass generates a surface gravity of 2.528 g, more than double Earth's. Jupiter's gravity has profound effects on the solar system. It can tear apart asteroids, capture moons, at least 67 are known, and may have prevented additional planets from forming in the early solar system. Some scientists believe Jupiter's gravitational influence disrupted the asteroid Vesta and continues to perturb Mercury's orbit, potentially ejecting it from the solar system in billions of years. Yet Jupiter also acts as a protective shield, deflecting or absorbing dangerous long-period comets that might otherwise threaten the inner